There's a proof so short you could fit it on a napkin, and it made a grown mathematician have a nervous breakdown. Not because it's wrong, because it's right, and nobody wanted it to be. The claim is this: some infinities are bigger than other infinities. And I know how that sounds. Infinity is infinity. It's the biggest thing there is. How can one be bigger? That was the reaction. Colleagues called it a disease. One of his old teachers spent years trying to bury it, and the guy who found it, Cantor, kept getting shipped off to sanatoriums while everyone argued about whether he'd broken math or just lost his mind. Here's the thing though. The argument he used is 4 lines. You do not need a degree. You need to count on your fingers and be a little bit stubborn. I got it wrong the first time I tried to explain it. So if it clicks slow for you, that's completely normal. We'll build up to it. But by the end of this, you're going to be able to prove yourself that there are more of some numbers than others, even though both piles never end. Keep your eye on that idea. It's the whole game. Okay, first we have to agree on what it means for 2 piles of stuff to be the same size. And this is going to feel insultingly obvious. Stick with me, because it's the trick the whole thing hinges on. Say I've got a bag of forks and a bag of spoons, and I want to know if there's the same number of each. One way: count the forks, count the spoons, compare. But there's a lazier way that doesn't need numbers at all. I just pair them up. 1 fork, 1 spoon, another fork, another spoon. If everything pairs off perfectly, nobody left standing alone, then the 2 bags are the same size. Full stop. I never counted anything. Watch the pairing. That's it. That's the definition. Same size means you can match them 1 to 1 with nothing left over. Now here's why that's sneaky. This definition still works. When the piles never end, I can't count to infinity. My fingers give out. But I can absolutely ask, can these 2 infinite piles be paired up perfectly? And that question has an answer. Sometimes yes, and sometimes, no matter how clever you are, no. That no is where things get weird. Let's test that definition on something that should break it. The counting numbers: 1, 2, 3, 4, forever. Now the even numbers: 2, 4, 6, 8, forever. Question: which pile is bigger? Your gut screams the whole numbers, obviously. The evens are only half of them. You literally threw away all the odds. That's what my gut said too. So let's pair them and see. Match 1 with 2, match 2 with 4, 3 with 6, 4 with 8. Every counting number n gets matched with the even number 2n. And here's what I want you to notice. Every even number gets used. Every single one. Pick any even number you like. Say 1,000. It's paired with 500. Nobody's left alone on either side. It's a perfect pairing, which by our definition means these 2 piles are the exact same size. The evens are just as numerous as all the whole numbers, despite being, in an obvious everyday sense, half of them. This is the first punch to the face. With infinity, a part can equal the whole. Throwing away half the numbers didn't make the pile smaller. Sit with how annoying that is for a second. Let me push on this, because once you accept that a part can equal the whole, infinity starts behaving like a mischievous roommate. Picture a hotel with infinitely many rooms. 1, 2, 3, on, and every room is full, completely booked. A new guest walks in. In a normal hotel, sorry, we're full. In this hotel, no problem. Everyone shifts down 1. The person in room 1 goes to room 2. Room 2 goes to room 3. Everybody moves up by 1, and room 1 is suddenly empty. New guest gets a bed, and nobody got kicked out. You can do this with a busload of infinitely many new guests too. You just have everyone move to double their room number, freeing up all the odd rooms, infinitely many free rooms, out of a hotel that was full. This isn't a trick with mirrors. It's the same fact as the evens. When the pile never ends, you can make room by shuffling, and the size doesn't change. So far, infinity looks like one single stretchy thing that absorbs everything you throw at it, which is exactly what everyone believed. One infinity. All the same, Cantor believed it too, for a while. Now we bring in the troublemakers, the real numbers. That just means every number on the number line, including all the endless messy decimals. Not just 1, 2, 3, but 0.5 and pi, 3.14159, and on forever with no pattern, and the square root of 2, and every random infinite decimal you could ever scribble. Between 0 and 1 alone, there are infinitely many of these. And I don't just mean a few fractions, I mean numbers whose decimal digits go on forever and never repeat, an unbroken smear of them with no gaps. So here's the natural question, and it's the one Cantor asked. We just saw the whole numbers and the evens are the same size. We saw the hotel swallow new guest whole. Can we do the same with the reals? Can we pair up the counting numbers 1, 2, 3 with all the real numbers between 0 and 1, 1 to 1, nothing left over? If yes, then infinity really is just one thing and we go home. If no, if there's literally no way to do it, then there's an infinity that's genuinely, provably bigger. That's the fork in the road. Let's actually try it. Here's how the proof works, and it's a classic move. We assume the thing we doubt is true, and then we chase it until it says something impossible. So, suppose it can be done. Suppose there is a perfect pairing between the counting numbers and every real number between 0 and 1. That means I can make a list. Number 1 on my list is some decimal. Number 2 is another decimal. Number 3, another. And because it's a perfect pairing, this list is complete. Every real number between 0 and 1 appears somewhere on it, at some position, with a definite spot in line. Nothing missing. That's what we're assuming. So let me just write down a list like that. First number, 0.1415, and so on. Second, 0.3333. Third, 0.7182. Fourth, some other endless decimal. And the list keeps going down forever. One row for every counting number. I don't care what the actual digits are. Pick any list you want. The claim on the table is that this list, whatever it is, contains all of them. Every real number is in here somewhere. Cantor's about to walk down this list and embarrass it. Watch this part. This is the whole trick, and it's beautiful. I'm going to build one new number, digit by digit, and I'm going to build it to be a troublemaker. For the first digit of my new number, I look at the first digit of the first number on the list. Whatever it is, I pick something different. Their first digit is a 1, mine's a 2. For the second digit of my new number, I look at the second digit of the second number on the list, and I make mine different from that. Their second digit is a 3, mine is a 4. Third digit of my number, third digit of the third number, make it different. And I just keep walking down the diagonal of the list, forever, down and across, one step at a time, and at every step I deliberately disagree with the number sitting on that diagonal. So I'm reading down this staircase of digits and flipping every one of them. When I'm done, and yes, it's an infinite done, I've got a brand new decimal, 0 point, and then my sequence of deliberately contrary digits, perfectly valid real number between 0 and 1. Now here's the question that ends the whole story. Is my new number on the list? Let's check. Could my new number be the first number on the list? No, because I made its first digit different from the first number's first digit. They disagree in position 1, so they can't be the same number. Could it be the second number on the list? No. I built the second digit to disagree with the second number's second digit. They differ in position 2. Could it be the 53rd number on the list? No, for the same reason. Its 53rd digit was rigged to be different. In fact, could my number be anywhere on the list, position n, for any n at all? No, because by construction, my number differs from the nth number on the list at exactly the nth digit. It disagrees with every single row in at least one spot. So my number is a perfectly good real number between 0 and 1, and it is not on the list anywhere. But wait, the whole assumption was that the list contained every real number between 0 and 1. And I just built one it doesn't contain. That's the contradiction. The list said it had all of them. It doesn't. It missed at least one, and I could do this again to catch that one, and it'd miss another. Let me say what just happened because it's easy to blow past it. We didn't fail to make a list. We proved that failing is guaranteed. Any list you hand me, no matter how clever, no matter how you order it, I can walk the diagonal and manufacture a real number you left out. There is no complete list of the reals. And remember what a list even is. A list is exactly a pairing with the counting numbers. First, second, third. So the reals cannot be paired one-to-one with the counting numbers. There are too many of them. They overflow. Both piles are infinite. But the reals are a bigger infinite. A strictly, provably no way around it bigger infinity. This is the moment infinity stops being one stretchy thing and splits in two. There's the countable infinity, the whole numbers, the evens, the fractions. Even they turn out to be this size, the stuff you can line up in a list. And then there's the reals, a fatter infinity that no list can hold. And the wildest part is the proof needed almost nothing, no heavy machinery, just a list, a diagonal, and the stubbornness to flip every digit. 4 lines, like I promised. So why the nervous breakdowns? Here's the human part, and it's rougher than the math. When Cantor published this in the 1870s and 80s, a lot of serious mathematicians didn't just disagree, they got angry. The loudest was a man named Leopold Kronker, who had been Cantor's own teacher. Kronker believed math should only deal with things you can build from the whole numbers in a finite number of steps. God made the integers, he said, all the rest is the work of man. And Cantor's completed infinities, these finished infinite piles you can compare and stack. To Kronker that was garbage. Worse than wrong, it was corrupting. He called Cantor a charlatan and a corrupter of youth, and he worked to block Cantor's papers and keep him out of the good universities. Cantor wanted a job in Berlin. He never got it. And Cantor, who was not a thick-skinned man, took it hard. He cycled in and out of depression, spent stretches in a sanatorium, and late in life drifted into strange obsessions, trying to prove Shakespeare was really Francis Bacon, that kind of thing. The math was bulletproof. The man was not. Being right early is often just a slower way of being alone. Here's the turn, though, and it's a good one. Cantor was right, and everybody knows it now. His theory of different-sized infinities, set theory, became the ground floor of modern mathematics. When you learn about functions or probability, or basically anything rigorous, you're standing on the thing Kronecker called a disease. David Hilbert, the biggest mathematician of the next generation, said no one shall expel us from the paradise that Cantor has created. Paradise. That's the word that won. But Cantor also left a loose thread, and I love that he did, because it means the story isn't tidy. He'd found 2 sizes of infinity, countable, the whole numbers, and bigger, the reals. So he asked the obvious next question. Is there anything in between, an infinity bigger than the whole numbers but smaller than the reals? He was sure the answer was no, nothing in between, and he spent years trying to prove it and couldn't. He called it the continuum hypothesis, and here's the part that still bugs me. We now know he couldn't have proven it, not because he wasn't clever enough, because it turns out you can't prove it either way. Using the normal rules of math, the question has no answer, but that, my friend, is a different video. So here's where we land. You now own a proof that some infinities are bigger than others. Not believe, own. If somebody doubts you, hand them a list, walk the diagonal, flip every digit, and watch their list fail. It works every time, forever, because that's what a proof is. And the thing I keep coming back to isn't even the result. It's how little it took. No supercomputer, no 1,000-page argument. A guy sat down, looked at an infinite list, and thought, what if I just disagree with all of you at once, 1 digit each? That's it. That's the entire weapon. And it was enough to split infinity in half and rewrite the foundations of math, even while the people in charge were calling him sick for it. The digit flip is the recurring character here, by the way. This diagonal trick shows up again in the deepest results in logic, the ones about what math can and can't ever prove. Same move, different costume. So keep it in your pocket. Next time somebody tells you infinity is just infinity, you know something they don't. And the one that still keeps me up, that gap in the middle, whether there's an infinity hiding between the counting numbers and the reals, nobody gets to know. On purpose, chew on that.